Okay, let's dive right into this explainer. Today we're going to uncover the engineering miracle that is actually driving the most powerful AI models right now. Because think about it, every single day, millions of us are interacting with artificial intelligence. We're asking chatbots to write complex emails, debug our code, maybe summarize massive reports, and we get a response back in literally seconds. It feels like magic. And honestly, most of us naturally just assume we're talking to one giant, singular, massive electronic brain. But the reality? It's much more complex, and frankly, a whole lot more fascinating. There's this hidden, highly specialized architecture working behind the scenes that makes all of this incredible speed and intelligence possible, and it does it without completely melting our computer hardware. So we really have to start with a fundamental question. It's basically the great AI scaling paradox of our time. We know that bigger models, and by bigger, I mean models holding billions or even trillions of data points, are just generally much smarter and vastly more capable. But here's the catch. Traditional scaling requires impossible amounts of computing power. And when we talk about crashing computers here, we're not just talking about your laptop freezing up and needing a reboot. We are talking about massive data centers that require their own dedicated power plants. We're talking millions of dollars in daily energy bills and physical hardware that simply overheats. So how exactly do we get the incredible brains of a massive AI without reaching a physical breaking point?
Well, to understand the solution, we first gonna have to understand the core of the problem. And that problem lies in what we call a standard dense model. In a traditional dense neural network, every single parameter is activated to process every single input. To put that in plain English, think of a parameter as a tiny connection or a learned rule inside the AI's brain. Now imagine asking a dense AI model to simply summarize a one-page document for you. To do this, every single artificial neuron in its entire massive billion parameter system has to wake up and read every single word. It is just an incredibly expensive, energy draining, and painfully slow way to get an answer.
Think of it like this. A traditional dense model is kind of like a lone general practitioner trying to diagnose every illness on Earth all by themselves. They're running from room to room, completely overwhelmed, frantically trying to remember the cure for everything from a paper cut to a rare genetic disorder. It is absolute chaos. On the other hand, a sparse mixture of experts model operates a lot more like a massive, state-of-the-art hospital. This hospital has highly specialized departments and a brilliantly efficient triage nurse sitting right at the front door. Instead of asking the hospital janitor, the leading cardiologist, and the payroll accountant to all gather around and examine a patient's broken thumb, we just use a triage system. We send that patient quickly and quietly only to the exact specialist who actually knows how to fix a thumb. And that brings us to the mixture of experts, or MoE. It's an AI architecture consisting of many specialist networks, where a router picks you answers. MoE completely replaces those traditional bulky, dense layers with a gate network, which is our triage nurse, and several distinct, smaller, expert neural networks. And what's really incredible here is that this router is a lightning-fast AI in and of itself. It's highly trained to do absolutely nothing else but evaluate your question in a fraction of a millisecond and instantly know exactly which specialists in the hospital are best equipped to handle your specific request. Let's actually break down exactly how this process works in practice. So, step one, a word fragment, or what AI researchers call a token, which is really just a piece of a word or short concept, enters the system. Step two, the router instantly evaluates that token. And step three, it sends the token only to the best suited experts. Now, interestingly enough, in a lot of models, it doesn't just pick one expert, it actually picks the top two. Why? Because it acts as a backup and beautifully blends specialties. It's exactly like having a cardiologist and a nutritionist briefly consult on a patient together. Meanwhile, all the other experts in the system, they just get to peacefully sleep using absolutely zero processing power. This actually brings us to a foundational concept that was introduced by researcher Noam Shazir and his team way back in 2017. They called this conditional computation, and it dramatically increases model capacity without a proportional increase in computation. This concept, which is also widely known as sparsity, is the absolute magic making modern AI possible today. It fundamentally breaks the traditional rules of computing where building something bigger always meant it had to be slower and way more expensive. With sparsity, you're essentially getting a multi-million-dollar supercomputer's worth of knowledge, but you are only paying the energy price of a standard laptop. To really grasp this, let's look at a concrete example that absolutely took the open source software world by storm. Mistral's incredible Mixtral 8x7b model has a massive 47 billion parameters in total. Think of that huge number as the total square footage of our AI hospital.
This gives the model immense capacity to store deep knowledge, perfect grammar, and highly complex reasoning patterns. Normally, trying to run a dense 47 billion parameter model would require incredibly specialized, super expensive data center hardware that no average person could ever even hope to have access to. But because of the mixture of experts architecture, the active parameter count tells a completely different story. Since the Mixtral model only routes your query to 2 experts at a time, it only uses the computing power of a 12 billion parameter model when it's actively generating text. It achieves top-tier genius-level performance while keeping the speed at which it generates answers, a process researchers call inference, incredibly fast. The math here is just brilliant. You get access to 47 billion parameters of smarts, but you only have to pay the computational toll for 12 billion. Section 2. MoEs in the real world. You might be thinking this is just theoretical lab stuff, but MoE is actually driving the biggest breakthroughs in the industry today. We already talked about Mistral's breakthrough model, but Google heavily uses MoE in their Gemini class models too. They use it for advanced embodied reasoning. And just for some quick context, embodied reasoning basically means an AI that actually understands its physical surroundings, which allows it to navigate complex real-world spaces, or even orchestrate multiple robots collaborating on a factory floor. Google also created the switch transformers, scaling this MoE architecture up to an astonishing 1.6 trillion parameters. Trillion with a T. That's a scale so massive it was practically unthinkable just a few years ago, and it is entirely thanks to MoE. But of course, no engineering miracle is completely perfect, right? We have to talk about the limitations. What happens if every single patient needs the cardiologist? In our hospital analogy, if a bus full of people with heart trouble pulls up to the emergency room all at once, the triage system completely breaks down. The waiting room backs up out the door, the cardiologists are completely overwhelmed, and meanwhile, the foot doctors are just sitting around in the back playing solitaire. In the AI world, this exact problem is known as the routing bottleneck. See, if the router sends everyone to the exact same expert, you get uneven load balancing. The processing dramatically slows down, and those underutilized experts just become dead weight. Actually, in some architectures, you even hit a critical failure called token overflow. This means if an expert is just too busy, it literally drops parts of your question, and the AI gets confused or starts hallucinating weird answers. And finally, there's a massive RAM requirement, because even though the resting experts aren't using active processing power, they still take up physical space on the computer's memory chips. Those memory chips, or VRAM, are incredibly expensive, making the actual hardware required to hold the model very costly. Thankfully, AI researchers are constantly innovating to solve these bottlenecks. Standard routing often tries to force equal balancing, but that runs the risk of forcing all the specialists to redundantly learn the exact same basic skills just to keep up with the load. DeepSeek, on the other hand, proposed a really brilliant alternative. They use shared experts that are always active to handle common, everyday core skills, like basic English grammar or maintaining a conversational tone. Then, they use routed experts that are only called upon for highly complex, peripheral skills, like writing intricate Python code or explaining quantum physics. It prevents redundant learning and keeps the whole system flowing incredibly smoothly. So at the end of the day, mixture of experts is the secret sauce keeping AI feeling like absolute magic without melting down the world's servers. As models continue to scale into the multi-trillions of parameters, we're quickly learning that intelligent efficiency and routing are honestly just as important as raw size. And it leaves us with a pretty profound question about the future of this technology. Will the ultimate future of artificial intelligence be a single, unimaginably giant brain? Or will it be a sprawling, hyper-efficient society of microscopic experts silently collaborating in the dark to answer our every question?
If you enjoyed this video, please like, comment, and subscribe for more AI and technology content. Thanks for watching.